What's up? Welcome to AP Exam Week. Yeah, I've been waiting to say that for a long time. And here we are ready to rock and roll. I want to talk to you a little bit about the schedule of this week. Things are a little weird. There was a tutoring session this morning. I hope you're one of the kiddos that was in there asking questions and learning. If not, there are two more sessions this week. There is the normal one, Tuesday, tomorrow after school at 3:30. And then there's going to be an abnormal one on Thursday. More on that in a moment, but the Friday morning one doesn't exist because it's supposed to start at 9. Your chem exam, the AP chem exam, starts at 8. And even if I wanted to get creative and hold a session before that, it would work against the idea of you getting sleep and breakfast. So there's no session Friday, but Thursday session will not take place at 3:30. Instead, it'll be taking place at 7 p.m. So that will be an evening tutoring session that will lighten the load of my constrictive parameters a bit. I'll be at my house, but we can get some work done. So make yourself a note. Thursday's tutoring is at 7 p.m. Same tutoring link for Thursday, though. All right, I want to do a couple more FRQs as a group. So let's dive in and tackle a little bit more practice. Give me a moment. All right, it's weird. Okay. All right, so just let me know if my screen freezes up or if you can't see something. But I would like to take a look at some kinetics is one that we haven't talked about. I had to remind myself to record because I was supposed to do it last period. But anyway, hey, look, it gives us a two-step mechanism. And really, out of all the FRQs we did throughout the school year, I kind of feel like this one was the most direct. I mean, you had to be pretty good at chemistry to do it, but there was definitely no wordy tricks at all. It like flat out wanted you to analyze a mechanism. So if you just basically knew your stuff, you could do it. But I'm going to write down the mechanism that it gives us. All right. And then it asks us 4 questions that I will ask out loud. Part A says, what is the balanced equation? All right. Now, I know that when balancing a mechanism, I'm looking for parts and different steps that match each other as reactants versus products. And those items will be deleted. Now, remember, they have to be exact copies of one another on different sides of the equation. So right away, for example, I see that chlorine and chlorine are the exact same on opposite sides. And the only other one is the ClO. All right. So to do the balanced equation, I'll bring down everything that's not crossed out, and it'll end up looking like this. And there is the equation. Part B wants us to start identifying vocab hidden within the mechanism. The first one is the catalyst. Remember, not every reaction has a catalyst, but by definition, if it does, the catalyst will be an item that is deleted as a product in the last step. Deleted as a product in the last step. So I would say that chlorine is the catalyst here. All right. I'd say because the amount at the end equals the amount in an earlier step. Part C asks about intermediates. All right. Now remember, an intermediate is going to be anything else that has been deleted in a different part of the problem. So in this case, obviously the ClO is the intermediate. All right, because it's produced in one step and consumed in another. Finally, part D gives us a rate law and then asks us to use it to figure out which step is rate determining, the RDS. It gives us this, so I'm just copying. And again, if you know the basics of rate law, this is not too difficult, because I know that the rate law is always based off the slowest step because that determines the rate of everything else. And it'll focus on the reactant. So obviously step 1 is the rate determining step as asked, because the rate law applies to the concentration of the materials in the slowest step. Now, it didn't ask for anything else, but if energy profile was mentioned, I'd like to remind you that the energy profile for this reaction would look something like this, because there's 2 steps of the mechanism overall. The first one is the slow step, the rate determining step. And in this case, we would have intermediates here, catalysts there. Lastly, let's focus on bonding. In this problem here, it gave us 4 different substances, and then asked us different questions about them. Now, they're wordy here, so I hope if you run into a similar question on the real exam, that you will pull them out and translate them clearly so you don't have to keep reading and thinking through them. So you'll see that right away, I'm gonna go ahead and take these 4 compounds. And I'm going to pull them out of there. So it gives me magnesium oxide, it says, iodine, chlorine trifluoride, and potassium chloride are the guys that we're analyzing. And then it asks us a variety of questions about them. The first question that it asks is what one is least ionic, the least ionic character. Now, I remember that covalent versus ionic character works on a sliding scale, with nonpolar being on one extreme, ionic being on the other extreme, and then polar covalent existing in the middle. Now, if something's going to be the least ionic, it's also the most covalent, right? So you'll notice that 2 of my given compounds are ionic, so I'm going to automatically ignore them for this part, because it's going to be one of these 2 covalent, non-metal only guys that is least ionic, and I want it to be the one that is furthest towards the non-polar side, because that's furthest from ionic. Nonpolar, of course, for us is defined as identical atoms only. So iodine is going to win this battle. The same lettered question also asks the opposite. Most ionic. So now we want to be at the other extreme, and I'm going to be choosing between the 2 ionic compounds. A couple things come to mind on the best way to tackle this. One of the ways that you learned is by focusing on the electronegativity differences. Now, the electronegativities would need to be given to you, but remember, if you take 2 squares and find the difference between them, the higher the difference is, the more ionic they are. In general, the further away the squares are from each other on the table, it makes them more and more ionic because they're getting so far away from being identical copies of each other. But using the actual values can be helpful. They usually don't make you do that. The other way we could look at it is Coulomb's law, because that equation is the same one that we use for lattice energy, because it deals with Q1s and Q2s. So let's talk a little bit about that. If I had an electronegativity chart and I compared the difference between magnesium and oxygen compared to the difference between potassium and chlorine, the larger difference would be magnesium oxide. So he is the most ionic. Now, if I was solving that from a Coulomb's law standpoint, it would be a charge comparison. All right, that's what the Q's stand for in this equation, is charge, right? So magnesium is +2, oxygen is -2, and if I compare those magnitudes with the other ionic compound, well, potassium's +1 and chlorine's -1, numbers that are smaller than these. And we know that this equation states larger charges give you larger products. So these numbers are bigger, which also points to magnesium oxide. Moving on to part B, it says, hey, let's draw some Lewis structure, yo, go a little Vesper crazy. And it picks one of our 4 compounds to draw. And the one that it picks is the chlorine trifluoride. It wants us to draw that dude there. Let's revisit our steps. I know that chlorine has 7 valence electrons. So does fluorine, times 3 is 21, for a grand total of 28 valence electrons. The central atom is usually the less electronegative, or the one that there is less of. All right, so we're going to call it chlorine in this case. We bond the leftover atoms to the central atom using single bonds. And then apply the octet everywhere, right? So we want 8 valence electrons on everybody, except hydrogen, who only wants 2, but that doesn't apply here. So remember that all of my single bonds are made up of 2 already. So each of the fluorines only craves 6 more. So now I'm giving all the fluorines their octet. Chlorine is still unhappy. He's sitting here with 2, 4, 6. So he only wants 2 more. And we could do that and go through our steps just for a little foresight though. Remember, we have to hit this number. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we're 4 short, not just 2 short. When we need to draw extra dots, remember our question becomes, can, in this case, chlorine expand his octet? Right? And the way that we answer that is we know that any element that has access to empty d orbitals can expand their octet. So can chlorine do it? Yes, because chlorine is in 3p block, meaning he's got access to everything with an energy level of 3, including the 3d block, which for chlorine is empty. So there's room to add extra electrons beyond the octet. And now we've got 28 total. The same lettered part of this question requests you to draw a dipole moment between one of the chlorine and fluorines. All right, so I'm just gonna blow this up over here. We're gonna bond a chlorine to a fluorine. And remember, the dipole moment looks like this, where we're going to point an arrow towards the more electronegative atom and put a tail there. I know fluorine is more electronegative because electronegativity increases right and up on the table, not counting the noble gases, right? Fluorine is the most electronegative anyway. And this is going to give fluorine a partial negative and chlorine a partial positive charge. Remember, the reason being is that the dipole moment is showing who is hogging the electrons. So fluorine is pulling harder on them. Those negative particles that he loves is giving him that partial charge. Finally, part C just flat out says, hey, I want a shape and angles. All right, another pretty much straightforward question as far as an FRQ goes, but you got to know your stuff. When you've got a central atom with 5 regions of electron density, 2 of which are lone pairs, the shape is automatically T-shaped.